Hey everybody, and welcome to the Continuous Kinetic Mixing Tech Talk. My name is Carlo De Los Reyes, co-founder and VP of Applications. I'm joined by my fellow co-founder and Director of Systems Engineering, Scott Goodrich.
Hey everyone.
And we're here to talk about a new process that we're introducing to DLP 3D printing, allowing us to print homogeneous fiber-filled parts efficiently. So as a quick refresher, we're a whole stack additive manufacturing company developing technologies and solutions across the additive stack, from hardware innovations, unique software algorithms, and next generation filled materials. All the technologies that we're developing are in support of our mission of building the world's most productive filled material additive manufacturing platform. This talk will focus on a unique hardware process that we have invented at Fortify called continuous kinetic mixing. In the composites world, what is paramount is to ensure an even distribution of particles and fiber in the matrix. This new process that we are introducing allows us to print homogeneous fiber-filled parts of any size quickly. So the use of fillers and fibers to augment the performance of a particular part is not a new concept by any means. We can draw many interesting parallels to the story of fiber reinforcement into the traditional manufacturing world, such as injection molding. When injection molding was first introduced to the world, the process was limited to single-phase or neat plastics. While adoption of the technology skyrocketed, its use was precluded from true engineering applications. Instead, parts such as toothpaste caps and shampoo bottles were manufactured en masse using this method. It wasn't until the introduction of fiber and other fillers that injection molded plastic components saw use in performance applications. This chart on the right of this slide is one of my favorite examples of why composites are so impactful. In the short span of just 2 to 3 decades, composite materials began to overtake metals as the majority material class used in commercial aircraft. This pattern can be seen throughout other industries as well. So, in short, composites allow for the augmentation of various material properties without sacrificing manufacturability of plastic components. At Fortify, we're borrowing from a very similar playbook. Similar to injection molding, we are looking to take a known manufacturing process that can scale and incorporate fillers to expand the market opportunity and applicability to engineering applications. So the manufacturing process that we've decided to build our platform around is fat polymerization, or more specifically, DLP 3D printing. 3D printing represents an excellent conduit for fiber-filled parts, as a combination of unique material properties with design for additive manufacturing principles can act as a force multiplier. However, the use of fillers in 3D printing have been limited to thermoplastic 3D printing processes such as fused filament fabrication or selective laser sintering. A big reason this is the case is that thermoplastic compounding industry is a mature industry dating all the way back to traditional injection molding feedstock compounding. Furthermore, as the feedstock for thermoplastic 3D printers are solid at room temperature, issues such as sedimentation and homogeneity are almost non-existent. That being said, thermoplastic-based 3D printing technologies have limitations in terms of part throughput and isotropy, as well as other thermal limitations. DLP, on the other hand, is a manufacturing platform that is known to scale. Groups in the industry are manufacturing hundreds of thousands of parts per year on similar technologies, and this is due to the parallelization capabilities combined with the layer masking approach that DLP allows. However, most photopolymers used on DLP platforms are limited to neat or unfilled systems due to the limited processing capabilities of commercial DLP printers. Because photopolymer feedstock is liquid at room temperature, sedimentation of filler material has precluded the use and development of fiber-filled photopolymers. And the filled materials that are available are all nanoparticle filled systems, which only improve stiffness, but not necessarily strength or other properties. So what others saw as a challenge, we saw as an opportunity to innovate. I'm going to pass it off to my colleague, Scott, to help explain the intricacies of CKM.
Thanks, Carl. So Fortify developed CKM to be able to print these challenging filled photopolymer systems with fibers that want to sediment out of the resin and high viscosities that are very challenging to print. On the left here, you can see the user pouring resin into the printer, where it's then brought into the CKM system and pumped up to our reservoir. Our printer automatically maintains the level of this heated, suspended composite material throughout the printing process, and the user just has to occasionally add material into that drawer, which is a non-disruptive process for high throughput printing of these composites. this basic schematic shows how our CKM system works. We have a mixer in the system in that drawer where the user is pouring that filled resin into that funnel that you see there. That resin is then heated in that mixer, circulated up to the reservoir, and maintained throughout the printing process. So what does this actually do for our ability to print challenging filled composite materials? When we first started Fortify, we were shooting to print these magnetically aligned composite materials. But as we got into that process, we learned in order to print aligned composites, you first have to print composites in the first place. We found ourselves bound in the lower left-hand corner of this graph where we couldn't handle resins that sedimented quickly or had very high viscosities. With CKM, we opened up that operating window to access materials like digital tooling and some of these low loss materials you see here that have fibers that sediment quickly and are very, very viscous. So by heating and suspending the fibers in these materials, we're able to maintain them in our printing process and print challenging composite materials. On the left here, you can see an example of this working. Without the CKM system, we see very quick sedimentation of our fiber out of our resin. So you can see the density of that polymer, of that composite, decreasing over time. Whereas with CKM, we are maintaining the density of that material over time and end up with a homogeneous print. On the right here, you can see an example of that in practice where without CKM, the fiber concentration throughout the print is changing on the part on the right there. On the part on the left, that was printed with CKM, and the fiber concentration throughout that part is homogeneous. We see this also in our microscopy and SEM data, where looking at layers, several thousand layers into a print versus early on in a print, we have identical fiber concentration and homogeneity, which really gives us the properties we're looking for out of these challenging composite materials.
Thanks, Scott. So, as you can see, there's a lot of interesting processes that we built in CKM. And so what does that get us in terms of applicability in 3D printing? So here we demonstrate the breadth of parts that we're able to print through the power of CKM. Using a ceramic filler, for example, we're able to print dielectric lenses that shape RF energy. Metal fibers, such as stainless steel, can be used to increase the thermal conductivity of components, such as in this generally designed heat sink. Lastly, ceramic fibers can be used to increase the wear resistance of high wear components, such as impellers. So we hope we've effectively conveyed the power of filled systems in this tech talk with the introduction of continuous kinetic mixing. Our engineers and scientists are working every day to develop next generation filled photopolymers to further expand the footprint of additive manufacturing. By combining the scalability of DLP 3D printing with CKM, we're building complex fiber reinforced parts at scale. So thank you for your time, everybody. If you have any questions about CKM or anything in general, feel free to shoot myself or Scott an email at our email addresses provided. Have a good rest of your day.
Thanks, everyone.